I'm going to speak about the effect of massive stars on their surroundings. So you see here on the left an image of the Eagle Nebula, which is a well-known galactic star-forming region. And on the right, this is the same image, but I added the X-ray image to compose the two images here. And you see the big difference between the two is that when you add this vision of the massive stars, you understand why the massive stars are shaping the surrounding. So I'm going to speak about this effect today. And so this was to visualize the point. So why do we care about this subject? So in fact, we know that high mass stars controls the galaxy's evolution, and so we would like to understand if H2 regions can really promote the formation of high mass stars. So we have about 7,000 ionized regions in the galaxy. And the question that we are interested in is to understand if the radiative feedback has a positive or negative impact on star formation. So when you look on the side of the models answers that the impact from H2 region will be negative on star formation. And what we see here, it's a model. So on the left, you have a real image of a galactic H2 region, and on the right you see the model. So the differences between the two is that in the model you do not have self-gravity, so star formation is not included in the model. But if you look only at the ionized region, you see that the models well reproduce what is observed in the galaxy. There are several models who try to explain what high mass stars do on the surrounding medium. And so we see in particular that modeling of the expansion of an H2 region in a fractal medium can lead to star formation in the surrounding. And there are also other models that predict that the impact of H2 regions on the surrounding should be negative. And so the idea is that from the model point of view, the feedback from high mass stars should stop star formation in the surrounding. Just to give a more clear view on what's going on, you have a first generation massive star at the center here, and then you will create an H2 region. Because the temperature between the two media, so the external part and the internal part of where the ionized gas is very different, you will have the expansion of the H2 region, and so you will create a shock front because the expansion is supersonic. And just behind the shock front, you will have an ionization front, and you will propagate the two in the surrounding medium. So you will collect a layer of material between the shock front and the ionization front. And if you look later in time, you will see that star formation is observed in this layer surrounding the H2 regions. And this is really what we observe in the galaxy. So the idea of what we are doing is to try to look on a multi-scale and multi-wavelength analysis of this topic of star formation, possibly triggered by H2 regions. On observations point of view, the idea is that we would like to detect first H2 regions. So we look in the galaxy and we search first for H2 regions. Then we study the young stellar population that is located around these H2 regions. We also study the associated molecular material, because this is from this molecular material that stars will form. And with the dynamics, so usually spectral lines and the velocities of these lines, we are able to really associate the young stellar object that we see with the H2 regions, and also to study the properties of the molecular material. So there are different kinds of study. We made in the past several statistical studies that show that when you look at the edges of an H2 region, here you have some examples, you clearly see an overdensity of young stellar objects in the layer that is located around the H2 regions. And on a more practical point of view, what you see here is that you have the main H2 region in red, and you see in the layer, in the surrounding, you see that star formation is ongoing with different stages of evolution. So you have young stellar object, you have here an ultra-compact H2 region, so this means that you have high mass star formation going on. And so you see different condensation. So you really have a layer where star formation is promoted by the expansion of the H2 region. On a statistical point of view, you can use the galactic surveys, so the Spitzer or the Herschel galactic surveys, to try to collect more information about what is observed around H2 region. So this has been done by Pedro Palmerim and collaborators. And if you do a statistics looking at H2 regions in the galactic plane, you will see that you have an accumulation of young stellar objects and very young stars at the edges of H2 regions. So this effect is really, on an observational point of view, it's really clear. So we decided to continue on this kind of study, and we recently published a new paper where we have decided to bias the selection of the young stellar object toward very young massive sources. So this is what we call the high mass starless clumps. And we do a statistic on this object and to try to see their properties when they are associated with an H2 region or non-associated with an H2 region. And we see clear differences. So here you have some examples of these massive clumps where at the moment no star formation is ongoing. So they are really early stage clump, but they are really massive. So we know that they will form high mass stars. And we look at their properties when they are located nearby H2 regions. And what we have found is that there is a clear difference in the properties of this high mass starless clump when they are associated with an H2 region. So to summarize, they are usually hotter than the other ones. They are more compact, more luminous. They are also more turbulent, and they really show different properties than the ones that are non-associated with H2 regions. Another important point is that when you look at these high mass starless clumps, they are usually connected to even denser density peak. And so we think that the filaments that are connected, those structures, can also play a role in star formation. So the main results from statistical studies that we clearly see an overdensity of young sources at the edges of H2 regions. They have specific properties when they are nearby H2 regions, and they are always found in a highly dynamical environment. We can also go to individual studies. So here we look at one specific H2 region in the galaxy. So this region is really located nearby and is located above the galactic plane. So the blue part is the ionized gas, and the surrounding is the colder material where you see ongoing star formation. So we have studied this region, and we saw that there are a series of condensation in the millimeter, and in these condensations we see star formation. ongoing. And so we can, with the Herschel satellite, we can study the young stellar objects that are observed in this region. And we can study the evolutionary stage of these sources depending on where they are located in the photodissociation region, around the H2 region. And we can have a closer look at a series of objects that are forming in the layer around the H2 region. We were interested in looking in more detail, so we use ALMA data to go inside those objects that were seen with Herschel. And so you see, for example, when you look at this source, you see that the source is fragmented when you lower the spatial scale. And you can really start to understand what's going on in the condensation. And in this object in particular, we detect a high mass star in the process of forming. So we are sure now that high mass stars are forming at the edges of H2 regions. To further study what is the impact of the ionizing star on the surrounding, we studied the filamentary structure that is around, can be found around H2 regions. And we saw that there is a clear compression when you look at the density profile of these filaments. And the compression comes from the incoming radiation from the ionizing star of the H2 region. So when you have this kind of compression, you will increase the density of the material and you will have better conditions to form higher mass stars. We have also been able to study this kind of phenomenon in external galaxies. So we went to the Large Magellanic Cloud to look at specific regions. So the interest of the Large Magellanic Cloud is that the metallicity is different. And so it's interesting to have a look. Here you have a Spitzer view of the region, and here I just put the field where we go for adaptive optics in the near infrared to really study the stellar content of these regions. And what you see here is that you have the ionizing stellar cluster at the center of this big extragalactic H2 region. And you see that in the surrounding, you have a series of very young stars directly connected to the layer around the H2 region. So just to summarize this part, we see that we see high mass stars in different evolutionary stage. We think that H2 regions limit the fragmentation of clumps. And we also saw evidence for radiative compression in the surrounding of H2 region. I just will speak briefly about a specific type of H2 regions that are the bipolar H2 regions, sorry. So here you see the case of a bipolar H2 region. So here, for example, you have a classical roundish H2 region. But if the high mass stars is forming in a filament where you have a clear gradient of density, then instead of having a roundish H2 region, you will have a bipolar H2 region. And this is really interesting also to study star formation. And we work on this subject. And what is really interesting is that you always have this configuration with the primordial filament that give birth to the first generation massive star. So it's really interesting to study the impact of H2 region in this context. So here is a small sketch to show what happens in bipolar H2 region and how the star formation developed in the filament. So what are the future prospects on this study, we are trying to better define the timescales of the star formation and the efficiency of star formation. We also try to better characterize the fragmentation and the compression of the H2 region on the star formation. And we recently saw that Gaia will give new evidence of star formation induced by H2 region by showing an age spread in the H2 region and using the Gaia clusters. And just to end my talk, I would like to mention, but I will not have time to develop it, that machine learning can really help in this kind of study. And so we are conducting at the moment a study on galactic filaments using machine learning and study star formation. And this really give very interesting results. And I will stop here. Thank you very much.
Thank you, Professor. Thank you very much.
Thank you. Yeah, thank you very much, Annie. Very interesting talk. And this work is subject to questions, discussion? No? I'm sorry. I would like to ask, you are looking for, or no, this star formation at the edge of the H2 regions produce mainly massive stars or also small stars, or we are not seeing the low mass stars because they are too low, or what?
No, we see both. We see both low mass star and high mass stars, but we were more interested in high mass stars because there is this connection with the re-ionization of the universe. So we would like to understand if you have this triggered star formation, and because the early universe was full of very high mass stars, we would like to understand if this triggering could have increased the formation of high mass star. So this was the point. But we do see a lot of lower mass stars at the edges of H2 region.
And they are at the same time with the high mass stars. I mean, I think that high mass stars produce another H2 region and turbulence in the gas and will not allow the formation of low mass stars.
In fact, you see in the PDR layer, this photodissociation layer, you see all kind of stars in all evolutionary stage. So, for example, we have cases where you have in the PDR you have compact H2 regions at place in the layer. And then you can see at other places, you can see lower mass stars. So you have all the evolutionary stage and all the masses together in the PDR.
Okay, thank you. Is there another question for Annie?